Okay, it's 8:30, so we'll get started. Good morning, everyone. Good morning for the last time, I guess, or I guess second to last time. We'll see you guys next week. So how's everyone doing today? All right. I know almost finals week, so everyone's stressed, but we're almost there. Okay, so the plan for today is we're just going to review for the final exam. So there's going to be no new content today. It's just old content. Okay. And so if you've had a chance to look at the study guide for the final yet, you should see that there are kind of four big areas that are going to be on the exam. Okay? So there's I do want to make half of the exam is going to be from the first midterm. So those are all the differential equation stuff. So I really want to make that a point of emphasis for this exam, just because ODE's differential equations is probably the most important thing to take away from this class. Because you're going to need it in vibration, you're going to need it in all your in heat transfer, if you're not in heat transfer right now. So I definitely want to make that a point of emphasis. So so we're going to go over second order ODEs and Laplace transforms today. So I definitely want to do those. From the second midterm, the only topic that I chose from the second midterm was Fourier series. And so all the stuff about vector calculus and Fourier transforms you don't have to worry about. And then of course all the recent stuff on probability and statistics. Okay. So my plan for today is, so obviously we're not going to be able to go through all of this just because it's a little bit too much to cover in one class session. I do want to review differential equations and Laplace transforms just because it's been a while since we've seen those. I'll probably skip over Fourier series just because we just had the exam on that, and generally people did pretty well on that part. And then we'll see how much we can get to with probability and statistics. Okay. All right. So logistically, the final exam, remember, it is next Thursday. So maybe I should write that down. It's going to be Thursday, May 18th at 9 a.m. It's about a 2-hour exam, and so you'll have until about 11 a.m. on that day, right? And it's going to take place in this room. Okay? So make sure you guys are. So it's almost the same time as our lecture time, just kind of push back. Okay. Okay. And so for the number of questions on the exam, there are 4 problem-solving questions. There are 6 short answer questions, right? So kind of just a little bit of a longer version of the midterm exam. In terms of what you can bring your writing utensil, so pen, pencil, whatever you feel comfortable with, calculator, and remember you can bring 2 cheat sheets, okay? So you can use both sides front and back, 8.5 by 11. So the cheat sheets are the same format as the midterm. You can just bring 2. If you haven't had a chance to pick up your midterms, I did bring both of them today. There are actually still quite a few that have left to be picked up. So if you haven't had a chance to pick it up, you can pick it up today. The cheat sheets are there as well from the first midterm. And so if you want to use that for the final exam, you're welcome to do that. Okay. All right. So I think that's all my announcements. Are there any questions I can answer before we get started with the review? Okay. All right, so let's go ahead and get started. All right, so our first kind of big topic for the final exam is going to be second order ODEs. So this was, I think, probably the first kind of big unit that we went over in the class. And so I know kind of for the first week we went over first order ODEs. But we spent a decent amount of time on second order. So hopefully these sound familiar. And by second order, what I mean is that the highest order derivative in the differential equation is second order derivative. And so the general form for it is the following. So we have our second order derivative, d squared y dt squared plus e dy dt plus qy is equal to sum right hand side r of t. So in particular, there's a very broad class of differential equations that we can solve, but the ones that we actually solved in this class were a very kind of specific class, okay? And they have to do with these coefficients. And so this P and this Q here, specifically the ones that we're trying to solve, these are specifically constant. Okay. And so they're not variables, they're not functions of t, they're not nonlinear. Okay. And so if you if you want to classify the types of problems that we actually solve, they're in linear, constant coefficient, second order ODEs. Okay. But that's kind of a mouthful. So you just say kind of second order. Okay. Okay. And so the main way that we solve these types of equations is we use the characteristic equation. Okay. So it was kind of a several step process, but let's kind of summarize how to solve this. All right, so first step. First step is to solve the homogeneous equation using the characteristic equation. Okay. And so if we have our differential equation like this, you have d squared y dt squared plus p dy dt plus qy, right? Remember, when I say homogeneous equation, what I mean by homogeneous is that the right-hand side is equal to 0. So we're going to set RP equal to 0. Okay. Just for now. A lot of times you're going to solve problems where the right-hand side is already 0. So you'll have to kind of break it out. But for the cases where we do have a right-hand side, where we do have a forcing function, the first step is just to set it equal to 0. And so to form the characteristic equation, we're basically going to take this differential equation and turn it into a quadratic equation, right? So we're going to replace all derivative terms with a corresponding polynomial. And so we have lambda squared. Lambda is usually the symbol that we use for this. So for the second order derivative, we make a second order polynomial, which is lambda squared. Then for the first order derivative, we bring down a linear term, which is lambda, but we also bring down the coefficient, right? So that p comes down as well. And the q just comes down by itself. Okay. So be careful with this. And so, this is one thing I kind of saw pretty consistently back, way back earlier in the semester. So when you're forming the characteristic equation, it's kind of tempting to take this y, right? And so you see that there's a y there. And so you would think, oh, I should make that into like a lambda, but don't do that, right? So the lambda, so the y by itself kind of just comes down as a constant term. So you should get kind of a pretty standard kind of quadratic equation. Okay. So once we form this quadratic equation, what we can do from here is we can find the roots of this quadratic equation. So that's going to give us two roots, so lambda 1 and lambda 2. So you can solve for the roots in whichever way that you want. If you're good at kind of factoring inside your head, then you can of course do that. Or if you're not sure, or if you can't think of the factoring in your head, you can always use the quadratic formula. So lambda 1, lambda 2 is equal to I'm going to use the symbols here. So it's going to be minus p plus or minus square root p squared minus 4q all divided by 2. Okay. You don't have to use a quadratic formula. If you can factor in your head, that's fine. But I know sometimes when you're in an exam, it's hard to kind of process those kinds of things. So having a formula that you can kind of fall back on is always nice. Okay. Okay. Right. So we're solving the homogeneous equation. We've found the roots. Okay. Now the problem kind of splits into 3 depending on the nature of our 2 roots. Okay. And so let's go over those 3 kind of cases. Let's review those 3 cases here. Okay. So case one is the simplest case. So in the case 1, we have 2 real distinct roots. Okay, so lambda 1, lambda 2 are both real numbers, and they're distinct from each other. Right. So when we have 2 real roots, our solution takes the form of 2 exponential functions that we just add to each other. E1 e and lambda 1 t plus e2 e the lambda 2 t. Okay. Okay. Case 2. So case 2 is a case where we have a repeated root. Okay, so we have our 2 roots are the same. Okay. So that would be the case where if you look at the quadratic formula up there, the quantity p squared minus 4q is equal to 0. Okay, because you get 2 roots that are just exactly the same. Okay. And so in this case, we still need 2 results or 2 solutions here that are linearly independent. And the way that we obtain that is we multiply the second solution by t. So you have C1 e to the lambda 1 t, okay, plus C2 t e to the lambda 1 t. So lambda 1 and lambda 2 are the same. So I just put lambda 1 twice. Right? And so of course the key difference here is that for our second solution, our C2 term, we're multiplied by t. Okay? And again, that was just to make sure that our solution is linearly independent. Okay. Case 3. And so you could have a situation where the quantity underneath the square root in a quadratic formula is negative. Okay? And so in that case, when you take a square root of a negative number, you get an imaginary. Right? And so case 3 is the case where we have a complex conjugate roots. Okay. So this is kind of an interesting case because we can form our solution with exponential just like we did in the first 2 cases. But when you have an exponential of an imaginary number, then it becomes a little bit complicated. And so typically the way that we present these results, or typically the way that we present the solution for complex conjugate roots is with sinusoids. Okay. And so this is what we say our solution is e to the minus p over 2t multiplied by t1 cosine of omega t plus c2 sine omega t Okay. Where omega, the frequency, is given by square root 4q minus p squared, all divided by 2. So in other words, the omega is basically the imaginary part of our root. So those are our three cases. And so, whenever you're solving a second order ODE, the first thing you're going to do is you're going to solve the characteristic equation. And then based on the roots, you're going to, form the homogeneous solution. All right. Any questions on this so far? Okay. All right. So one thing, of course, one thing you'll notice in all these solutions is that there are arbitrary constants here, right? So we have C1 and C2 in all of the solutions. So remember, those C1 and C2 are arbitrary constants. And the way that we solve for them is by applying our boundary conditions. Okay, but you have to be careful. So I thought this a lot back then too. So when we have kind of a complex problem with the forcing function, a lot of people would kind of stop right here and apply the boundary conditions to solve for C1, C2. Okay, but you can't do that yet. And so when your RT is not equal to 0, you have to wait until you solve for the particular solution before applying the boundary conditions. Okay. So that's going to be the next. That's going to be the next step. But I just kind of wanted to remind you what C1 is. Okay. And just a bit more trivia. And so, if you kind of remember back when we discussed second order ODEs, we spent a lot of time comparing it to a mass spring damper system. Okay. And so each of these three cases here actually had a physical interpretation in terms of what that actually looked like for the solution. Okay. And so for the case for two real roots, this is the case where we had an overdamped solution. Because that occurs for cases when we have a lot of damping in the system, so the solution kind of damps down very quickly. Okay. For the case when we have a repeated root, this is a critically damped system. And then the case for complex conjugate roots, this is a underdamped situation. Okay. So that's step one. Okay, so the step one to solving these differential equations is solve the homogeneous equation, and then get this result here. Okay. Step two. But once we have the homogeneous solution, now is the time to solve for the particular solution that goes with our forcing function RT. Okay. And so if we go back to our original equation here, so our original equation was d squared y dt squared plus d dy dt plus uy equal to r of t. Okay. The RT refers to the right-hand side of the differential equation. Basically, any term that's not multiplied by y or its derivatives. Okay. And so there's a part of the solution that's going to correspond to this RT here. Okay. And that's what we have to do here. Right? Okay. So there are a few methods that you can use to solve for this particular solution. I think a couple people kind of used variation of parameters, which is probably you learned that in 250p. So that's totally fine. But the only method that we had time to kind of cover in class was the method of undetermined coefficients. Okay. And what undetermined coefficients basically says is that our particular solution has the same functional form, or it looks similar to our forcing function RT. Okay. Let me do this. So y p of t is approximately equal to r of t. Okay. And so it's kind of hard to explain this method kind of in general. So kind of the best way to kind of show this is with a few kind of quick examples. So let's say that RT is a polynomial. And so let's say RT is let's just take this 8 t squared minus 4. Right, so the form for this equation, you can say, is that it's a polynomial function because it has powers of t or simple powers of t. Okay. And the maximum power or the order of this polynomial is 2. Okay. But we use order for quite a few different things in this class. So I'm going to try not to use it here. So we'll say that this is a polynomial function with a quadratic term. And so what that means is that for our particular solution, yp, that means it's also going to be a polynomial function with a quadratic term. And so the form that I would guess for yp in this case is that it has to have a quadratic term, e squared. Okay. But we don't know exactly what the coefficients are for this. And so that's hence the name for this method is undetermined coefficients, right? And so for this t squared, I'm going to put an unknown coefficient a in front. It's going to be a t squared. And then what I'm going to do from here is I'm going to include all in lower order polynomial terms as well. Okay, so we have a t squared bt plus c. Okay. Right, and then what we say is that that's the most generic quadratic function that we can take. Okay. And so once you know the form, or once you kind of guessed the form for yp, what you are then going to do is you're going to take this and take the derivatives of this and plug it back into the original differential equation. Right, so then once you do that, what you can do is then you can use that equation to solve for all the coefficients. Right, and so what you're going to get in the end is you're going to get a functional form, or you're going to get a solution for y. Okay. From here, you can form the full solution. So you can take what you got from step 1 and you can just add it together to what you got from step 2. We have y of t is equal to yh of t plus yp. For yh of t, this is from step 1. And yp of t, this is from step 2. Okay. Any questions on this? It's a long process. It's a lot of steps to solve these differential equations. And so, I know it's these aren't the most fun problems to do, but if you guys leave this class and you don't know how to solve these types of equations, half the department is going to beat the shit out of me. So you guys really need to know how to do these problems, okay? All right, so that's step 2. Right, so last step when you're solving these second order differential equations is to finally apply your initial conditions. Okay. And this is what's going to solve for your unknown, your arbitrary constants in your homogeneous solution. Okay. All right, so for these types of problems, for second order ODEs, I'm always going to give you 2 initial conditions, and they always kind of have the same form. And so the first initial condition is going to be what we call the initial value. So it's going to be phi of 0 equal to something. Let's say this is y naught. And then the second initial condition is always going to be a derivative condition. So it's going to be y prime of 0. That's equal to y not prime. Okay. All right. And so for this step, basically what you're going to do is you're going to take your full solution and apply it here. And so when I say full solution, that includes both your homogeneous solution and the particular solution, right? And so for the first condition here, you're just going to simply plug in t is equal to 0, okay? And that's going to give you your first equation. And then for the second condition, you're going to take the derivative of your full solution and then plug in t is equal to 0. All right, so what this is going to give you is that for these two conditions here, it's going to give you two equations. Okay, and those two equations are going to let you solve for C1 and C2. Right, that's a three-step process of how to solve these second order ODEs, right? So step one, solve the homogeneous equation. Step two, solve the particular solution if it's there, right? So sometimes I'm gonna give you a homogeneous problem, you can just totally skip step two. Okay? But in the case where it is there, you're gonna have to solve for it. And then step three is to apply the initial conditions. All right, any questions on this? Okay. All right, one last kind of conceptual topic that I want to review before we move on to the class is the concept of resonance. And so resonance, when we talk about resonance, what we particularly mean is these are situations where we have an applied forcing to our differential equation. Okay? So in other words, these are cases when we have an RT function. Okay. And so without getting too much into the specifics, or at least the mathematics, I would say, what can happen sometimes that when you have a very particular forcing function that has a particular frequency. Okay. And this particular frequency is one that matches the homogeneous solution in an underdamped case. So as an example, let's say that we have an underdamped system. So for an underdamped system, we have YH of T is equal to E to the minus P over 2 T times C1 cosine of omega T plus C2 sine of omega T. Okay. Where that omega is equal to 4Q minus P squared 2. Okay. Right, that was our case 3 for our homogeneous solution. What I want to focus on here is the omega. Okay. Because if you have a forcing function with the same omega, so let's say RT, okay, it doesn't even have to be both sine or cosine, it could be just one or the other, right? So let's say R omega is A0 cosine of omega T. Okay. So if the frequency of the forcing is the same as what we call the natural frequency of the system, okay, then resonance is going to occur. And so what is resonance? And so resonance, in a nutshell, resonance is bad. You usually don't want resonance to occur. Okay. Because what resonance is going to do is going to cause very large amplitude response, and that often is going to break stuff. Okay. So one example of this that we talked about, I believe is in the homework assignment. So I think it was a conceptual problem in homework 2. Was that if you've ever seen this trick, and I think I linked the video there too, where like people can shatter a wine glass with their voice, right? And so you have very trained opera singers, or even just normal person too. If you sing at a wine glass at a very particular frequency, right, a very particular pitch of their voice, then what can happen is that the wine glass is going to shatter. And that's not a function of the volume, right? And so, one thing people, or I'd say the most common misconception is that when you see that happening, you're like, oh, that person's voice is super loud. And so that's what shattered the glass. It has nothing to do with volume, it has to do with resonance, right? So they're hitting a very particular pitch to cause resonance in the wine glass. Okay, so it's going to be, it's matching the natural frequency of the wine glass, which is eventually causes it to shatter. Okay. All right, so I wanted to review this because I think when people talk about resonance, you think a lot about Fourier series, and there is a lot of overlap, but resonance is kind of something a little bit different. So I want to make sure you guys kind of know that heading into the exam. Okay. Any final questions on second order ODEs before we move on to Laplace? Yeah.
We go over linear independence and if a function is linear.
Sure. Yeah. Yeah, so linear independence. Linear independence has to do with the fact that, when we solve a second order ODE, or at least for the homogeneous solution, we get two solutions, right? Okay. And so these solutions we obtain from the roots of the characteristic equation. And so in order for those two solutions to be valid, they have to be what we call linearly independent. Okay. And so linear independence it's a very fancy term that we use, and it has a very strict kind of mathematical definition. But for our purposes, what I want you to kind of take away from this is that those two functions or those two solutions that we get, they can't be the same solution. Right. So this requirement here, it's really only relevant, or it really kind of rears its head for the case when we have a repeated root, right? And so when we have a repeated root, we only have just kind of one root to the characteristic equation. Okay. And so from that one root, we can form one solution. So we say y1 of t is equal to e to the lambda 1 t. Okay. Normally, what we would do in this case, at least for the case for the two real roots, is that we have y2 is equal to e to the lambda 1 t. which is the other root, you could say. So it's two of the same root, but it's the same root twice. And so, we can say that y2 is equal to the same exponential function, e to the lambda 1t. Okay. All right, but we can't have this. And so we can't have two functions that are the same, right? So we have here two exponential functions and their exponent is exactly the same. So we can't have this because we need our two solutions to be linearly independent. And so to rectify this and to get around this, basically what we do is we take the second solution and we just multiply it by t. Okay. It seems like a very simple trick. There is a kind of a strict kind of mathematical proof for this. I don't remember if we did it. We may have skipped it back then. But basically, this is the trick that we do. So now our two solutions here are linearly independent. So we have y1 is an exponential function, and y2 is t multiplied by an exponential function, and that's enough to kind of make them different from each other, at least in a linear sense. Yeah. So for all the other cases, for case 1 and for case 3, we get two linearly independent solutions just automatically. But for the repeated root, we have to do this kind of extra step here by multiplying by t. Does that answer your question for? All right, any other questions on second order ODEs? Okay, all right, so let's move on to Laplace. Okay. So our next big unit after second order ODEs was Laplace transforms. Okay. And there was a lot to Laplace. We spent quite a bit of time on it. And so I'm gonna try to speed run this. And so but the main idea that I want you to obtain from Laplace was that it was an alternative method for solving differential. And so when you have a differential equation, one way that you could solve it is you can go through the 3-step process that we went through above. Okay. Or another way is you can do the Laplace transform. And so the Laplace transform way kind of has the following methodology. Okay. So step one. Step one is to take your differential equation and take the Laplace transform of that entire equation. Okay. And remember, the way we take Laplace transforms, there is a formula for it, and so you can perform an integral to take the Laplace transforms. But the most common way that people use is that they use the table. Okay. And so for the exam, I'll provide you the table. So just like the first exam, I'm going to give you the table for that. Okay, so you don't have to write that on your cheat sheet because it kind of takes up a lot of real estate. And I know you probably you have better use for your cheat sheet than that. Okay. So I'll provide you the table. Okay. And so you're going to take Laplace transform of that entire equation there. Okay. Step two, okay. And this is kind of the nice thing about Laplace that people generally like is that now you can solve an algebra problem. Okay. So algebraically, algebraically, you're going to solve for the solution to the ODE. In other words, you're going to solve for y of s. That makes it sound very simple, but it's actually a lot more work from there. Okay, so technically this is all step 2, right? And so if you look in the textbook, they say this is step 2, and then step 3 is just take the inverse and profit. But there's a lot more to this, and so I like to say that there's a step 2A here. And so the step 2A often involves partial fraction decomposition. Okay? Because what you're going to get from step 2 is you're going to get some very complicated, fractional algebraic expressions. And then in order to actually invert that back to the time domain, you have to do some partial fraction decompositions, and you may have to do some other kind of weird algebra stuff. I want to mention that because I think that's the part that kind of scares people the most. Okay. And so after performing partial fraction decomposition, what you're going to have is you're going to have an algebraic expression that is much more tenable and much more easy to invert. Okay. And so step 3. Step 3 is to take that algebraic expression and invert it using the table. Okay. And so it's kind of the inverse of kind of what we did before, step 1, you're basically looking at the left side of the table and going to the right, or the step 3, you're going to look at the right side of the table, the Laplace expressions, and then convert it back. And so ideally, you're never going to use the formula for the Laplace transform. You're always going to use the table to do that for you. Okay. So that's kind of the 3-step process. I don't want to dive too much into the theory, because I think the thing with Laplace is that you kind of have to see a bunch of examples to kind of see it through. Okay. So I want to do one example of kind of what I call kind of basic Laplace. And then what I really want to go over is step and impulse functions, which is where Laplace really shines. Okay. But that's a 3-step process that we're going to go through, and I'll show you what that looks like in an example. All right, any questions on just the beginning parts of Laplace? Okay. All right, let's do an example. All right, so this is an example. I don't think we had time to go over it in class, but it was in a handout. Okay. So this example here, we have y double prime minus y prime minus 2y is equal to 0. And our initial conditions is we have y of 0 equal to 1, y prime of 0 equal to 0. Okay. All right, so we have a fairly standard differential equation. So technically we don't have to use Laplace for this. And so we can solve this using our normal method. But let's see what it looks like in Laplace. Okay. So let's follow our 3-step process to solve this equation. All right, step 1. So step 1, we're going to take the Laplace transform of this entire equation. As we have our equation here, y double prime minus y prime minus 2y is equal to 0. Okay. we're going to take the Laplace transform of the entire. And the way I denote the Laplace transform is I use this kind of fancy L. Okay. So we're going to take each term individually. So remember, Laplace is a linear operator. And so whenever we have terms that are separated by a plus or a minus, we can do those individually, right? And so this is going to be Laplace transform by double prime minus Laplace transform prime minus 2 Laplace transform all equal to 0. Laplace transform of 0 is still 0. So we'll just leave that as that. All right, so let's go ahead and evaluate these expressions here. So let's take Laplace transform of y double prime. And so this is something that's in the Laplace table. But if we look up in the Laplace table, this is equal to s squared big Y of s minus s y of 0 minus y prime of 0. Right. So everything in the parentheses there, that's the Laplace transform of y double prime. Next, we're going to take the Laplace transform of y prime. So this would be s big Y of s minus y of 0 minus 2. And then the Laplace transform of y is just big Y of, and all this is equal to 0. Right. So the next step here is going to be to plug in the initial conditions. And so you can see that one thing that Laplace does well is that it directly incorporates the initial conditions. So you don't have to add it in a separate step. It's all kind of naturally part of the process. Okay. And so we go back up to the problem here. We can see that y of 0 is equal to 1. So everywhere we see y of 0, we're going to plug in 1. We have y of 0 in two places here, so we're going to plug in 1 here and 1 there. Okay. And then our other initial condition is y prime of 0 is equal to 0. And so everywhere we see y prime of 0, we're just going to plug in 0. Okay. And so we only have one location for y prime of 0, which is here. And so we plug in 0, we're just going to cancel that guy out. Okay, so let's go ahead and simplify this expression. So we have s squared y of s minus s times 1 minus s y of s plus 1 is 2 s to 0. All right, so that's step 1. All right, step 2. Step 2 is we're going to solve this expression for y of s. Okay. And so the way we're going to do this is that we're going to keep every single term with y of s, we're going to keep on the left-hand side and just factor out those factor out the y of s. And then everything without y of s, we're going to move to the right. Okay, so we have two terms here that don't have y of s, and so we have a minus s here and a plus 1. Okay, we're going to move those to the right-hand side. And so on the right-hand side, we have an s minus 1. Okay. And so that's what we get just by moving those terms algebraically over to the other side. And then on the other side, we have squared s minus s y of s minus 2 1. Okay. And so we factor out y of s from that. We have y of s by s squared is s is 2 is equal to s minus 1. All right. So now let's divide both sides by s squared minus s minus 2, and that'll give us our expression for y. 5s is equal to s minus 1 divided by s squared minus s. Okay. So step 2a, and so right now, we have an expression here that's not quite ready for inverting. Okay, and so we have to do some partial fraction decomposition to kind of prepare this. All right, so let me write out y of s again. So we have y of s is equal to s minus 1 up top. One thing that's going to help us is that I'm going to factor out the denominator. Okay, and so that is a quadratic expression, and so we can separate this into s minus 2, s plus 1. Right, and so the goal of partial fraction decomposition is that we have that denominator, right? So we have two terms in the denominator that are multiplied by each other. So we have s minus 2, s plus 1. Right? Individually, we would be able to invert those, but when they're multiplied together, we can't really do anything. Okay, and so we need to decompose this denominator into separate terms. Okay. And so what we say is that this expression here is going to be equal to two fractions that are added to each other. Okay, the first fraction is going to have s minus 2, which would be the first term in that denominator, and then the other term is going to have s plus 1, which is the other expression. Okay. Of course, we can't just magically do this, and so in order to kind of make this mathematically consistent, we have to have arbitrary constants up top. So we have a and b. And so the goal of a partial fraction decomposition is to solve for the values for a and b, such that this expression is consistent. Okay. And so the way we're going to do this is we're going to multiply this entire equation here. So we have, basically what we set up is an algebraic equation. Okay. So we're going to multiply this entire equation by the shared denominator. Okay. And so if we do that, we get s minus 1. We're going to multiply this entire expression by s minus 2 times s plus 1. Okay, so we have s minus 1 is equal to a times s plus 1 plus b s 2. Okay. All right, and so we're going to multiply the right-hand side through, and we're going to group it in terms of s and constant equations. If s minus 1 is equal to as plus a bs minus 2b. And so if we group the like terms here, we have s minus 1 is equal to s multiplied by a plus b plus constant term 1 times a minus 2 All right, so this is going to give us two algebraic equations, and so we have our S term here, is we have A plus B. This has to equal to 1 here. Okay. And so this is the equation that we obtained from the S term. And then from the constant term, what we get is A minus 2B equal to minus 1. All right, so this gives us two algebraic equations, which we can use to solve for A and B. And so if we solve for these two, we get A is equal to 1/3 and B is equal to 2/3. Okay. I'm going a little bit faster just because I want to make sure we get to step and impulse functions. And then I have just something very brief to say about the probability statistics part. So we're very quickly running out of time. Okay. And so for these expressions for A and B, we get is y of s is equal to 1/3 times 1 over s minus 2 plus 2/3 times 1 over s plus 1. Okay. Okay. So this is really good here because now what we have in y of s is that these two expressions here we can invert very easily in the table. Because we look at this first expression here, we look at this expression here, both of these show up in the table. And so finally we get to step 3. Step 3 is to invert. Yes. Okay. And so if we do that, we look it up in the table. You get y of t is equal to 1/3 plus inverse of 1 over s minus 2 plus 2/3 plus inverse of s plus 1. Okay. And so if we look these up in the table, what we get is y of t is equal to 1/3 e to the 2t. There. Plus 2/3 e to the minus. That is our solution. All right, any questions on that example there? So I think the thing with differential equations and Laplace, yes, I think the solution methods, they do take some time. These are not really short problems. You have to follow kind of a lot of steps. But what I tried to do for both differential equations and Laplace is that I try to break it down into each kind of step for you. And so if you ever feel like you're lost, then if you follow kind of the steps in the process, then it'll kind of get you towards this. And so what I would recommend is that, I was very kind of careful with how I did it today, is that if you look at the differential equations part and the Laplace part, we had a three-step solution procedure for each one. Right? So I would recommend on your cheat sheet, write those 3 steps. And so for a differential equations problem, these are the 3 steps that I have to do. For a Laplace problem, these are the 3 steps I have to do. And then, if you write those 3 steps, even if you don't have room for an example on your cheat sheet, as long as you have those 3 steps and you kind of, you try to follow them, you're going to get close. You're going to get close to the solution. Right? If anything, it'll help guide you if you're cutting lost. So I think what's easy to happen during these solutions is that you kind of get lost in the middle of it. You get lost in the algebra. You get lost in kind of the the integration or whatever. As long as you have those 3 steps, it's kind of easy to kind of find. Okay. So one more thing I wanted to say about Laplace is step and impulse functions. spell. All right, so step and impulse functions are kind of where Laplace really shines. And so when we talk about step and impulse functions, what I mean is that these are kind of special forcing functions that that you can use for your differential. So what step and impulse functions allow you to do is that it kind of opens up the possibilities in terms of the different types of forcings that you can do. Okay. And we use step and impulse functions for kind of two very specific types of forces. Okay. And so for step functions, we use these to model forcings that can be turned on and turned off. Okay. Because if you draw a step function, it looks like the following. So we have our p-axis here. A step function, some people call it a square wave, a square pulse, or a rectangular pulse, if you want to be more precise. Okay. It looks like that. Okay. And so when the square wave turns on, or when the step function goes up, this is when we're turning on the forcing. Okay. And when the step function goes down, this is like where we're turning it off. Those step functions are really good for this. Okay. And of course, I bring this up within the context of Laplace, because when you have a forcing function that has either a step or impulse function, you kind of have to solve it with Laplace. It's actually a lot more annoying to solve it than normal. Okay. And so when you have a forcing function that has, remember the symbol that we use for the step function is U. So as an example, let's say that we have a forcing function that looks like this. Consistent. Right, and so we have a forcing function that's turned on at t is equal to 4. So we have 5 of u times t minus 4 minus 5 times u of t minus 7. And so this wave is turned off at t is equal to 7. Okay. When we take the Laplace transform of this, and so we compute r of s, for step functions, it looks like the following. And so, on the one hand, 5 here is just a constant, so I'm just going to bring that out in front. The Laplace transform for a step is just 1 over s. Okay. We have 5 over s here. But because of this t shifting, right? So remember, these step functions are always shifted by an amount t. We have to account for that t shifting using an exponential term. So this is e minus 4s plus 5s. Our second step function here is shifted by 7. So we have e to minus 7s. Okay. These exponentials here, these represent our t shift. All right. that's step functions. Impulse functions, those are the other kind of special, that's the other special function that we went over. Impulse functions are used to model forcings that happen kind of very, very quickly. So if you were to plot a impulse function, it would look basically like this. Okay, so it's something that spikes up very quickly and then it dies down. Okay. So impulse functions are used quite often, and if you kind of recall back from way back maybe 2 months ago, we use impulse functions to model things like maybe like a hammer blow, right? So maybe you have an object and you hit it with a hammer. Okay. So the hammer is only going to make contact with the object for just a very brief instant. And so that would be one thing you can model with impulses. Another thing, if you want to look at an electrical example, maybe like a surge in a circuit. Okay, so that's something that can be modeled with impulses. Okay. But basically anything that occurs very quickly that's going to cause a response in your system, that can be modeled with impulses. And so the Laplace transform impulse function is actually even simpler. And so the only thing we have is just the t shift, right? So we have e to the minus a s, where a is the amount that we shift. Okay. Okay. So fortunately, I wish we had time to do an example with step and impulse functions, and in fact, that's what I plan to do. But at the very least, I want to introduce it kind of conceptually to you guys, just so that you can use it. Okay. One last thing I want to say. One last thing I want to mention today, that we didn't have time for probability statistics, but I do want to let you know, because probability statistics is always kind of a wild card for this class. I do want to kind of limit your studying, so you're not kind of looking over the whole thing. Okay. I would say conceptually, there's a lot more conceptual things of probability statistics to know. Okay, so definitely make sure you focus on the conceptual part. But there is going to be one problem-solving problem on the exam with probability statistics. And I will tell you kind of, it'll be either one or two type of problem. They're both pretty easy. I'd say this is probably going to be the easiest 15 points on the exam that you'll do. Okay. So there are two types of problems that I can ask you for probability statistics. Okay. There's either confidence intervals. Okay. So I would give you a set of data, and I would ask you to compute the confidence intervals on this set of data. Okay. And the other type of problem I can give you is hypothesis testing. So, again, I would give you a set of data, and I would say this is a hypothesis, and I would want you to test whether or not that hypothesis is validated by the data or. Right, because realistically, those are the only two things I can test you on, because you're not going to have access to a spreadsheet, and so we can't do any kind of advanced statistics or anything like that. But even just with the calculator, you should be able to do those things. Okay. All right, any final questions on this before we wrap up the review?
Yeah. We're gonna get all the distribution value.
Yes, yeah. So so I'm going to give you a sheet. It's going to have a Laplace table, and then the t distribution values for the normal. So, yeah, you don't have to put that on the sheet. Okay, all right. So before you guys go, so I just want to say this is our last class session together. So I want to take the chance to just thank you guys for a great semester. I know this class has been kind of a tough time slot, and I honestly, when I come to class every day, I'm like half asleep too, because I teach really late on Monday, Wednesday. So I want to thank you guys for coming every day, and thank you guys for just a great semester. Thank you guys for being patient with me. You know, I know I make a lot of mistakes, especially in the homework. So thank you guys for being patient with me. And you know, hope you guys have a good summer. You know, hopefully I'll see you guys. I'll see a lot of you guys next year for your classes too. But thank you again, and it's been a pleasure. If you guys haven't picked up your midterms yet, I have them in the front here. If not, you know, if you can't pick it up now, I'll have them in my office again after that too. And then yeah, I'll see you guys for the final next week. Sure. Yeah. Yeah. Exactly. Yeah. And you're going to want to use an opposite distinction because the way the distributions are defined, always define less than. No word. Yeah. Alan, any final questions before I wrap up the call? Okay, all right, we'll see you next week.